Hello, everybody. My name is Andy Rivenes. I'm going to talk to you today about database and memory, real-time analytics supercharged. So I'm going to do the first part of the presentation, and then Shashank Shavan, who's our Vice President of In-Memory Technologies, is going to do the second part of the presentation. So let's talk a little bit about why you should use database and memory. So database and memory, the use case is analytic reporting. So the traditional use of it is for your existing reporting applications, whether that's third-party tools, existing applications that do reporting, BI type, business intelligence type applications, because you don't have to use or you don't have to change your applications, and you can make use of database and memory for significantly improved reporting performance. But the more exciting thing, I think, is the ability to use or do real-time analytics with database and memory, and that is running analytics right on your source data. And so not having to wait for that data to be ETL'd or transformed or transferred to maybe a decision support system or a reporting database or waiting for that data to go to your data warehouse, you can actually run your existing or new, perhaps, analytic reporting right on the source data without having to wait for that data to be moved somewhere else. It can be very powerful for companies to get their information in real time. And then lastly, database and memory, since it doesn't use analytic reporting indexes, very often, especially with mature applications, you can drop those analytic reporting indexes and see a significant speed up in both performance, because now your DML or your insert, update, and delete transactions don't have to maintain those indexes, but it also frees up space, no more generation of undo and redo, and you don't have to back that space up to, or those indexes up to make them recoverable. So it can provide a considerable capacity benefit, workload reduction by being able to drop analytic reporting indexes that you might not need now with database and memory. So let's talk a little about what is database and memory. So traditionally, Oracle database has been a row format database, very good for transaction processing, not as conducive to reporting. We have to look through too much data. In other words, we have to traverse each row, find the columns we're interested in to do reporting. Indexes can help with that, but it's much better for transaction processing, the row format, than it is for reporting. Columnar formats, which aren't new, columnar formatted databases have been around for a very long time, but columnar formats are very good for reporting. You only have to look at the columns you're interested in. It compresses well and it vectorizes well. Not so great for transaction processing, though, because we have to kind of stitch that data or those column attributes back together into rows in order to be able to operate on them for transactions. Now, with database and memory, you kind of get the best of both worlds. You get row formatted data and columnar formatted data. We haven't changed the Oracle architecture, so Oracle's still a row format-based database. All transactions occur in the row format, but what we've added is we've added an in-memory area and the ability to have columnar formatted data as well. So we keep that data simultaneously and transactionally consistent. You don't have to change any of your applications to take advantage of it. It's still Oracle database, fully integrated with all the existing features of Oracle database, but it really now allows you to have some significant performance improvements for analytic reporting. Very simple to implement. One initialization parameter, in-memory underscore size. You set that enables database and memory and allocates the in-memory area or the column store, if you will. Then you just alter tables, partitions, subpartitions, or materialized views to be enabled for in-memory. In the background, we asynchronously populate that data into the column store, and then the optimizer can take advantage of that data based on cost, if it makes sense to access that data from a column store. What if it makes more sense to access that data from row store? Maybe you're only looking for one or two rows. Maybe you're doing insert, updates, and deletes. Then that data will be accessed from the row store. That's why you don't have to change your application SQL to take advantage of database and memory, because it's an optimizer cost decision at execution time. In addition to that, then you can later go back and drop those analytic reporting indexes I was talking about and possibly free up some additional capacity, and away you go. So how does database in memory work? So as I mentioned, database in memory is a columnar format, or provides a columnar format. It's a pure in-memory columnar format. Since it's a columnar format, it compresses well. Our default compression typically gets about a 2x compression rate. You can get anywhere from 2x to 20x compression rate. There are multiple levels of compression. It's available on all hardware platforms, so it's not just Exadata or just a specific hardware platform. Basically, anywhere Oracle database runs, you can run database in memory. And one of the really nice things about it is you don't have to put the entire database in memory. Most folks aren't running around with terabytes of memory in their database servers. So you can pick and choose the objects, as I mentioned earlier, the tables, the partitions, subpartitions, materialized views. You can pick and choose those objects to populate in the column store based on your analytic workload and your business requirements. We do have something called the In-Memory Advisor, which can help determine what objects to populate in the column store. And then if you know your workload, you can obviously do it yourself. The in-memory area is actually part of the SGA. So again, we haven't changed the Oracle transaction architecture. When you set the in-memory underscore size parameter, we'll allocate memory out of the SGA. One of the things I tell folks is not to steal memory from, say, the buffer cache or the shared pool. You're likely to impact the workloads that depend on those sizes. We want to think, since this is the in-memory part, we want to think of adding additional memory to the database server in order to support in-memory. So again, that's the in-memory part of database in memory. And then I'll talk just a little bit about the technology. Since it is columnar in format, we can access just the columns that are part of the query, can provide a significant speed up. We compress well. I mentioned compression. We have multiple levels of compression. So again, anywhere from 2x to 20x. We support something called in-memory storage indexes. So based on filter predicates, we can skip over data that we know that won't have, won't be part of the query. And so the fastest way to do something is really to not do it at all. It's very similar to Exadata storage indexes. And then SIMD vector processing. So we support single instruction, multiple data. We can compare multiple values at the same time. Think of it as kind of like array processing versus one row at a time or one column value at a time. So if you have a filter predicate, we can make multiple comparisons at the same time. Basically, that takes us from being able to scan millions of rows per second per core to billions of rows per second per core. It can give us an order of magnitude speed up in our scan performance. In addition to the underlying in-memory technology and those features, the optimizer also understands database in memory. As I've mentioned, it's a cost-based decision at parse time whether we access the data in the row store or in the column store. In addition to that, the optimizer has some tricks that it can perform. Specifically, when it's scanning data, it can push filter predicates and function-based aggregations into the scan of the data and perform those operations during the scan. Actually, the optimizer doesn't do that, but in memory does, but it's part of the execution plan, and which can be much faster than having to return the row or column values and process them after the scan and throwing away those values. So we can actually do it during the scan. We can turn a hash join into a scan and filter operation, especially in the case of filter predicates on one of the, say, the smaller of the two tables. When we do a hash join, we can create Bloom filters. And so we can actually do turn the hash join into a scan and filter operation rather than having to go to the probe table in the PGA to probe for the join. And then lastly, in-memory aggregation or vector group by. So we supported sort group bys and hash group bys. Now with database in memory enabled, we can support a vector group by. What that buys us is the ability now to do not only the join of the tables, but also the group by aggregation during the scan of those tables. So that can give us a significant performance boost for group by aggregations. So we have the ability to do scan and filtering aggregations, function-based aggregations during the scan, changing hash joins into scan and filter operations, and then group by aggregations and turning those into scan and filter operations. And so that together, that provides significant performance and benefit for queries that can take advantage of database and memory. So why not just cache the table in the buffer cache? I get asked very often, what if I just put the entire table or object in the buffer cache? That's in memory. Wouldn't that be the same as having database in memory? And the answer is no, and this is an example. So we have here a query against our line order table, and we're just looking for the max total order price. The table's fully populated in the column store, and that query runs in 1/100th of a second, very fast. The same table, the line order table, is also fully cached in the buffer cache in the keep pool. And notice the no in memory hint. So we're telling the optimizer, don't do a table access in memory full, just do a table access full. And that query runs over 8 seconds, memory to memory, row versus columnar format. Much more powerful to have database and memory enabled. How do you know which queries will benefit? So what I like to tell folks is, for a non-trivial amount of rows in execution time, if the majority of it, or if a significant amount of that time is spent accessing data, joining data, or group by aggregations, then database and memory is going to provide benefit. But you have to target the right workloads. So we've talked about analytic reporting workloads. Database and memory isn't going to speed up insert, updates, and deletes, or DML. It's not going to speed up row by row or slow by slow processing. So if you're pulling all of the data out of the database and processing that in maybe PL SQL, if it's in the database but in row format, or in your applications in your middle tier, we're not going to speed up that part of it. We're only going to speed up the access, the join, and the aggregation in the column store. So think set-based processing. And that's really where our target is for database and memory. Does it work with other database features? So with Exadata, we have some unique features with database and memory. Database and memory, DRAM, we can populate data in the column store. With Exadata, there's terabytes of flash, and you can also populate that data, or that data can be populated in flash cache in database and memory formats. So this now gives you the ability to have terabytes of columnar formatted data, or if you could think of it as tiers of columnar formatted data. In addition to that, on Exadata, we support something called in-memory fault tolerance, or duplication. So we can mirror IMCUs, or the in-memory data, the columnar data in DRAM. We can mirror that across rack instances. So on Exadata, if one of the instances were to go down, that data would still be in one of the other instances. This is the in-memory part. If an instance were to go down, the data that's in memory isn't going to be available. But if you're mirroring it with duplication on Exadata, you can still process that data in memory on the other surviving nodes and still maintain your SLAs. In addition to that, we support Active Data Guard. So on a standby database, you could actually run your analytic reporting there and take advantage of that standby on Exadata, and you can populate the same or different objects in the standby column store than what you have in your primary column store. So Active Data Guard is fully supported on Exadata with database and memory. And all flavors of Exadata. So whether you're on premises, in the cloud, cloud at customer, wherever Exadata is and database and memory runs, you can take advantage of these additional features. In addition to that, we support multi-tenant. So in 21C, you only have multi-tenant, you only have container databases, but database and memory works with container databases so that PDBs can access the column store in the container database and can allocate objects and populate those in the column store for each of the different PDBs, or single or non-container database if you're still on 19C and not taking advantage of multi-tenant. So it works with or without, very flexible, which is kind of one of the parts of database and memory that really makes it easy to integrate into your existing environment. We take care or work with all of the existing Oracle technologies, whether it's RAC, multi-tenant, parallel query, partitioning, everything that you might be leveraging with Oracle technology, you can still leverage with database and memory. Database and memory also supports, as I mentioned, DataGuard, Golden Gate, RAC, ASM, RMAN. So all of your existing recoverability, backup technologies, those all work seamlessly with database and memory as well. So let me talk just briefly about what's new with database and memory. So database and memory first came out with 12.102 of Oracle database. Since then, with 12.2, 18C, 19C, and now 21C, we've added significant features, additional features to database and memory. I think the takeaway is that we've improved performance and manageability, but it's also an actively developed product. So we're continuing to make new changes and provide new features for database and memory as we go along. With that, that concludes part one of my talk on database and memory. And now Shashank will take over with part two. Thank you.
Thanks, Andy. We're going to spend the second half of the talk now discussing real customer use cases and discuss how they achieve significant value using in-memory. But first, let's talk about what real-time enterprises are and why they need in-memory now. Real-time enterprises are customers whose businesses depend on being data-driven, agile, and efficient. They need to react instantly to changing data, and they need to move swiftly to beat out their competition. And they have to do so efficiently to save on costs. Retailers, for example, want to use location-based analytics in real time to quickly send a mobile coupon to a customer that fits a certain profile. Another driving factor for using database and memory now is the hardware trends we're seeing in the industry today. For example, memory is becoming larger and cheaper, networks are becoming faster, and we're seeing larger multi-core processors with beefier SIMD vector processing units. All of these hardware technologies are helping enable in-memory processing. So let's look at three customers who are using in-memory today with different hardware configurations and very different use cases. We have Lufthansa, Steph, and Hisense. Lufthansa, as many of you know, is an airline company based in Germany and with operations worldwide. Steph is a company headquartered in France that is a cold logistics company that deals with connecting different players in the food industry. And many of us know Hisense as a company that makes electronic products like TVs. But they're also giants in the home appliances section in general. So let's begin with Lufthansa. What's their use case? Well, Lufthansa has over 4,500 aircrafts and more than 70 airports. Every 6 to 10 years, a D-check operation is performed on an aircraft. The aircraft is nearly completely disassembled and every single part is examined and determined if it needs to be repaired or not. It takes 4 to 6 weeks and around 30,000 to 50,000 person hours to complete the operation. And as you can imagine, tracking is very important. For example, which component was sent for repair? Where is it actually? Is it during transport? Is it at the repairs at the warehouse? And will it be usable again and when? All of this information is stored in Oracle in a database that they call the tracking database. Now, business users will generate reports with queries like, hey, how long does it take to repair an engine? How long did it take to transport the engine? So how did in-memory help Lufthansa? Well, first, their daily reporting queries improved by as much as 100x. They also were able to drop their analytic indexes, which saved on disk space. And what in-memory features and technologies did they use? Well, they first and foremost used the in-memory advisor. Now, the in-memory advisor is a tool that analyzes your workload and makes specific recommendations on how to size the in-memory column store and which objects should be placed in memory. It's been available since Oracle 12c and is often the first thing we advise customers to run in getting started with in-memory. They also saw very good compression. They leveraged a memcompress level within memory called memcompress for query high. And at this compression level, they were able to get up to 33x compression. They also use a feature called in-memory dynamic scans. Now, with IMDS, you can parallelize your table scans dynamically on top of whatever PQ, DOP, or degree of parallelism you're running at, which makes sure you don't let idle CPU processing go to waste. With in-memory vector group by, we optimize group by aggregation over joins in a truly novel way, where the group by operators are pushed down into the table scan operators. And lastly, Lufthansa leverages the foundational features of in-memory. And what we mean by foundational features are the features that came with in-memory on day one, which are SIMD vectorization, in-memory storage indexes, priority-based population. These were the three main ones that they ended up leveraging in their workload. Moving on to Hisense now. Hisense, as I mentioned, is a global enterprise company in the household items and consumer electronics space. They use SAP ERP system for both domestic and their international business. The domestic business runs on traditional hardware, and their overseas business runs on Exadata. And prior to that, it was running on the Sun T5 systems. So now they have month-end processing period where business analysts run literally millions of queries to generate reports. And this leads to resource contention and queuing delays with reports taking forever to complete. The situation is exasperated by the fact that they are seeing close to 200 gigabytes per month data growth due to increased business. So how did in-memory help Hisense? Well, one of the biggest benefits of in-memory is that it is completely transparent to the application. No changes were needed to the SAP ERP application they were using, and Hisense really appreciated that. Another major benefit they saw was the amount of compression they can get. They went from 1.5 terabytes on disk to just 133 gigabytes in memory to hold their tables. And they saw up to 41x compression in some cases for some tables. Now, Hisense saw their monthly closing analytic queries improve by up to 3x, and they estimated that over 8,000 hours can be saved each month based on how fast their queries ran within memory. And when they upgraded to Exadata and used in memory, even with a 16% increase in load, they saw the average execution time decrease by 2x. Now, what in-memory features and technologies do they use? Well, first, they found it very useful to use the compression advisor. The compression advisor could be used to best assess how much compression they will likely get if they move their tables into the column store. They also use the in-memory advisor, like Lufthansa, as a starting point, both during evaluation for their POC as well as during production. Hisense also leveraged the in-memory duplicate feature that's available only on Exadata. With duplicate mode, in-memory tables are duplicated across the rack cluster, enabling high availability and faster performance with always local access. Hisense also found the in-memory distribute for service feature very useful. Hisense populates on one instance of rack, and they query using serial execution. And then in the event of a failure or an instance being shut down, they would then repopulate on another instance, and they would start running their queries there. Now moving on to STEF. STEF is a European leader in the food industry supply chain. And they have the same. Everything you have in your fridge or freezer goes through STEF operations. They provide temperature control logistics and transport services. So they take food from a producer or farmer, for example, and they transport it in these temperature controlled trucks to distribute to different players in the supply chain, for example, packaging or distributor or retailer. Now, business managers need detailed and daily reports from the IT department to manage the activity that's going on, such as support decision process, warehouse management, etc. There are multiple data marts that are maintained, and these data marts are refreshed daily with new updates so that business decisions can be made in near real time. So this is an HTAP workload. HTAP meaning hybrid transactions and analytics processing workload. Daily data processing can last 6 hours with an average throughput of 250 DML operations per second. And all the while, there are analytic queries running simultaneously. And they have a star schema workload with several large fact tables, in some cases, more than 2 billion rows. Now, how did in-memory help STEF? Well, out of the box, they got 10 to 100x improvement with no additional changes. And this is, again, in an HTAP environment where heavy analytic scans are mixed in with 100 million updates a day. Step IT has queries with lots of joins. Within memory, join processing is accelerated using the SIMD vectorized algorithm for Bloom filtering. Now, because they are a mixed workload environment, they'll have dirty IMCUs. Dirty IMCUs are IMCUs which have newly inserted or updated rows. It's very important that we repopulate dirty IMCUs quickly to make them available for analytic queries. Now that's where double buffering and incremental repopulate come into play. With double buffering, we continue to make the dirty IMCUs available to queries, but while in the background, we build fresh new IMCUs that will eventually replace the dirty ones. With incremental repopulation, the idea is to simply build a new IMCU using the contents of the old IMCU wherever possible, and that saves on overall population time. And lastly, we have trickle repopulation. Trickle repopulation is a mechanism that allows us to periodically refresh all remaining dirty IMCUs in the background at a slow and steady pace. Step IT also makes use of fast start, which is a feature that enables the database to open faster by storing columnar data on disk. And like with the other two customers, they use the foundational features heavily: SIMD vectorization, in-memory storage indexes, etc. Where can you get more information? Well, we have a database in memory blog. We also have a database in memory hands-on lab. And of course, online, there's plenty of documentation. So with that, Andy and I would like to thank you for listening into our presentation and wish you well. Thank you.